All right, today we're going to see how a computer adds numbers. So computers can do many simple things very fast, and doing math is one of the things that it does really well. But how does it actually do that? Using transistors. So we use some circuits called half adders and full adders. We're going to talk about those right now. So if I'm adding binary numbers, let's say that I want to add 0 plus 0, that would be obviously 0, right? If I'm adding 0 plus 1, that would be 1. If I'm adding 1 plus 0, that would also be 1. But if I'm adding 1 plus 1, that's 2, but 2 in binary is 0, 1. So if I look at it, right, it's going to take my output is going to take 2 bits to display if I'm adding two 1-bit numbers. So just like if I have $2 in my wallet, it's the same as 0, 2, same as 0, 0, 2. You can put a bunch of leading zeros, doesn't change anything. So same as 0, 0, 0, 1, 0, 1, 1, 0. So check it out. When I look at the first one, right? 0, 0 yields a 0. 0, 1 yields a 1. 1, 0 yields a 1, but 1, 1 yields a 0. So whenever they're different, whenever I have a 0, 1, a 1, 0, whenever they're different, they yield a 1. So the XOR gate, if I'm doing that in the circuit, that would be an XOR gate. Remember the XOR gate, whenever I have, if you look at the truth table for an XOR gate, whenever I have two different numbers, it gives me a 1. If I have the same, it gives me a 0. Okay. If I look at the carry, kind of like as I carry the number out, 0, 0 gives a 0, 0, 1 gives a 0, 1, 0 gives a 0, 1, 1 gives a 1. So it only gives me a 1 when I have a 1, 1, when I have 1 and a 1. So an AND gate. An AND gate. So this guy would be your answer. And in computer terms, they call that Y. Who knows why? This guy is going to be the carry. So we'll call that CO for carry out. So to add 2-bit numbers, this would be the circuit. Okay? And we can try some different scenarios. So by example, if I go in and I put, let's see if I have a different color pen. I have a blue pen. Okay, so if I put 0, 0, right? 0, 0 on the input of an XOR gate would be 0 out. 0 goes down here to the AND gate. 0, 0 on an AND gate is 0. So basically, if I have 0 plus 0, I get, when I look at my 2, I have my answer, Y, and I have my carry out. Both of them would be 0. If I go in and I add, let's say, 0, 1. 0 plus 1. Now I have 0, 1 on the XOR gate would be a 1, and I have 0, 1 on an AND gate would be 0. So my carry is 0, my Y is 1. So 0 plus 1 gives me an answer of 1. If I go in and do 1 and 1, 1, 1. So 1 plus 1, I go and I'll have 1, 1 on an XOR gate right here. 1, 1 on an XOR gate gives us 0. So my answer is 0. Also get 1, 1 on the AND gate. 1, 1 on the AND gate is 1. So I have 1 right here. So 1 plus 1 is 1, 0, or 2 in binary. So that's the half adder circuit. All it is, it's an XOR gate and an AND gate. So that's all good. But what if I need to add more than one bit at a time? So if I have, for example, 0, 1, 1, 1. So I need to add 1 and 3 should be 4, right? So check it out. If I add 1 plus 1, okay, that's going to be 2, but there's no 2, so I put a 0 and I have a carry. So now my 0, 1 is 1 plus the carry from the last time would be 2, which is 1, 0. So 1 plus 3 is 4. So I need to have a carry when I add more than one bit. So we use what's called a full adder circuit to do that. So I have my carry in, I have AB is going to be the two numbers that I add, and then I'm going to have my answer, which we call Y for whatever strange reason, and then I have a carry out. So I have to do that, I have an XOR gate, I have an AND gate, I have an XOR gate, I have an AND gate, and then I have an OR gate for the carry on. So basically my answer goes into an XOR gate. I also XOR it with the carry in. That becomes my answer. Okay, my two numbers that I'm adding on an AND gate and the carry on and the answer for that in an AND gate, or those two together, and I get my carry out. Okay, so to show really how that works, let's add two numbers. So if I need to add two 1-bit numbers, so kind of like two, I guess two 2-bit numbers, I need two of these full adders together. So I go in and I look at it. This guy is a full adder right here. This guy is a full adder right here. So I have a full adder circuit for the first bit. I have a full adder circuit for the second bit. So let's try to add those two together. And when you hook them up together, the carry out from the first bit, from the ones, goes to the carry in on the twos. Okay, so let's go in and try to do an example for that and see if it works. Okay, so I go in and I have, what should we add? Let's go 0, 1 plus 0, 1. So if I have 0, 1 plus 0, 1, right? So 1 plus 1 should be 2. 1 and 1 right here is 2. So it's 0 with a 1 carry. 1 plus 0 is 1. So 1 plus 1 should yield 2 if I go through this example. So I go in, I'm going to have on the first ones, on the ones, I'm going to have 0, 1. On the twos, I'm going to have 0, 1. So basically, I'm doing it wrong. I'm going to have the 1 position. These are the ones. These are the twos. So I'm going to have 1, 1 on these guys. I'm going to have 0, 0 on these guys. So basically, the 1 position right here and the 2 position right here. All right, so let's go in and do it. In the very start, I don't have anything on the carry. I do not have a carry. So if I go in, I go on this guy. So my 0 goes to, if I follow the line, to this XOR, and it also goes to this AND gate right here. Okay, my 1, 1, bam, bam, and then it goes down to this guy. So 1, 1 on an XOR gate is 0, bam. 1, 1 on an AND gate is a 1. So now I'll come up here. I have 0, 0 on my XOR gate, which gives me a 0. I have 0, 0 on an AND gate gives me a 0. And now if I move this guy, see the 1 from this AND gate, 0 or 1 gives me a 1. So basically my answer, right, the first digit, it's going to be my y for the ones, is going to be 0. So I have a 0 y for the ones. Okay, my carry is a 1 right here. So now I go down, I have a carry right here. So now I have 0, 0. I come in, 0, 0 gives me a 0 right here on the XOR gate. So now I have a 0, 1 on a XOR gate gives me a 1. I come down here, I have a 0, and I have a 1 on this guy, and a 0 on this guy gives me a 0. I have a 0, 0 on an AND gate gives me a 0. 0, 0 on an OR gate gives me a 0. So my 2 position is a 1. It's going to be my Y 2 position. And then my carry out is a 0. So if I have another carry right here, that would be a 0. So I added 0, 1 plus 0, 1 leaves me 1, 0, and I don't have a carry. So that is how a computer adds numbers. There's another video where it kind of shows that also, that I'm going to show you right now the rest of. So let's see kind of the rest of that video right there.
For the output to be on as well. If both switches are on, or if both switches are off, the output will be off. Now, what makes up this exclusive OR gate? Well, it's an OR gate, a NAND gate, and an AND gate. Well, what's a NAND gate? That's just an AND gate with a NOT gate on the back end. A NOT gate just flips whatever the output is to its opposite. In other words, the NAND gate is only off if both inputs are on, the exact opposite of the AND gate. This is the key part of the exclusive OR gate. Now let's see how this works when we turn just the top switch on. The OR output in the exclusive OR gate is on, and the NAND output is on, so the AND output is on as well, and therefore the right light bulb is on. Now, if we turn the top switch off and the bottom switch on, we'll get the exact same result. If both switches are on, though, the exclusive OR gate is off, but the separate AND gate below it is on, causing the left light bulb to be on. In other words, 1 plus 1 equals 1, 0. In reality, though, when you add decimal numbers, such as 7 and 7 to get 14, the 1 is considered the number that has to be carried to the next column. And in fact, that's just how it works with binary as well. Normally, you would have several full adders right next to each other. The left light bulb next to our full adder would actually be the number that carries to the next full adder. So let's remove the left light bulb and run that wire down to the next full adder as the carry out, while at the same time accepting a carry in wire from the previous full adder. This carry in wire is why we need another half adder in order to make our full adder. The 2 separate AND gates in our half adders connect to an additional OR gate at the bottom right, which then powers our carry out wire. So here our 2 switches are already on. And if the carry in wire from the previous adder is also turned on, then we are essentially adding 1 plus 1 on our 2 switches plus the 1 on the carry in wire, or 1 plus 1 plus 1, which in binary equals 1, 1, or 3 in decimal. The 1, 1 can be seen here because our light bulb is on and our carry-out wire is on as well. If we turn off the carry-in wire and turn off our 2 switches, then our output wires are off as well. Now let's just focus on the full adder as a unit, which we'll just call an adder from this point on. And let's label the wires. We'll use A and B to represent the input from our 2 switches, and sum to represent the wire to the light bulb. Now let's remove the switches and the light bulb, turn the adder on its side, rearrange our labels, and then zoom out. Now we have 8 adders next to each other, and let's label them from right to left with letters so that we can talk about them separately. We'll add 2 switches above each of our adders to represent our A and B inputs, and then we'll connect a light bulb to each of our sum outputs. The light bulbs again can be labeled with their decimal equivalents 1, 2, 4, 8, and then you just keep multiplying by 2. 8 times 2 is 16, times 2 is 32, 64, and 128. Let's now add an area on the left to see what we're doing. We'll first put the binary numbers that our switches and light bulbs represent, and then a plus sign to represent the adders, and then we'll add the equivalent numbers in decimal form. Finally, we'll put numbers on the adders themselves, showing the current state of each wire coming into the adder and going out, 0 or 1, off or on. Now let's see what happens when we add 1 plus 1. Well, in adder A, the A and B inputs are both 1, and the carry in wire is off. So it's 1 plus 1 plus 0, which in binary equals 1, 0, causing the carry out wire to be on and the sum wire to be off. So then in adder B, the A and B inputs are 0, but the carry in input is 1. So the sum line on adder B is on, causing the 2 light bulb to light up. So 1 plus 1 equals 2. You'll begin to see a little bit more about how this works as we do some more examples. Let's look at 2 plus 2. In adder A, none of the inputs are on in this case, so neither the sum nor the carryout wire is on. Adder B, though, has inputs A and B on, so the carryout wire from adder B is on, which then becomes the carry in wire to adder C, causing the 4 light bulb to light up, showing that 2 plus 2 equals 4. 3 plus 3 causes adder A on the far right to carry out a 1, which then causes adder B to have to add 1 plus 1 plus 1, which in binary equals 1, 1. So both the sum wire of adder B and the carryout wire of adder B are on, causing the light bulbs under adder B and under adder C to both be on. So 3 plus 3 equals 6. Let's look at a few more examples for you to consider on your own. We won't talk through these, but feel free to pause the video and take a longer look if you'd like. Here is 10 plus 10. Now let's look at 15 plus 12. And finally, 219 plus 36, which adds up to the maximum of our light bulbs, 255. Now, this kind of thing happens millions of times a second inside of the microprocessor that fits on the motherboard inside of your computer. So now you've seen how computers add numbers in one lesson.